Greetings and welcome back. We are moving to a different part of session 5. We are still talking about data representation. We have learned that data could be represented in the form of a vector. And we could potentially visualize the data in a 3D space. We could potentially place them in a scatter plot. The more we make it visual, the better our brain is going to process that. With that in mind, let's begin the next part. Let's have the screen share. This is what we have at the moment. Graph and network representation. So once again, we are trying to introduce the tools that a data scientist need to use them, right? So technically speaking, we may not be actually utilizing the tools we are discussing now in this class. A more advanced data science course potentially are going to utilize those tools. But since this is elementary course, you are supposed to know these terminologies, these tools and representations available to you. So let's begin. You're going to hear a lot in several research papers and several project discussion points that you're going to be dealing with graphs and matrices. So take a look at this one. We are going to call this undirected graph. The reason we call it undirected is because, as you can see, between D and A, I didn't tell you whether it's going to go from D to A or from A to D. I didn't mention any direction on it. So that's why it's called undirected graph. This is a connectivity graph. And the adjacency matrix is going to be created out of the graph. The reason we want to do that, because at some point we want to do a reverse process. We have a visual connections and we want to represent that for the computer to understand. So if you take a look at that, I have A, B, C, D, E, F, G. So I'm going to list them horizontally and vertically as the label of my columns and row. A, B, C, D, E, F, G, A, B, C, D, E, F, G. So I have the two-dimension matrix at the moment. Now, obviously, the connection between A and B is going to offer me 1. 1 means that there is a connection. And at this time, A to B is 1, but also B to A is 1. There is no direction on the graph. A is connected to C, A is connected to E, A is connected to B, and A is connected to D. So B, C, D, E, F, as you can see, we have 1, 1, 1, 1, 1. And similarly, in a mirror fashion, basically the diagonal is going to act like a mirror in this case. And this one is going to be represented by this one is going to be represented by this one, and that's going to be undirected graph. Based on the rules we identify while programming the code, we basically tell the program this is undirected graph and this is how you're supposed to deal with the graph. Now, directed graph has an arrow on the connectivity lines. So for example, D goes to E, but E doesn't go to D. With that in mind, or for example, B goes to C, but C doesn't go to B. With that in mind, the mirror property is not going to be available. So A is connected to B, but B is not connected to A. So we are going to say 0. At this time, we are assuming that none of the nodes are actually connected to itself. And as you can see, none of the nodes actually have a self-directed line. So that's why the diagonal component is going to be all zeros. A is not connected to A, D is not connected to D, and so on. This is my diagonal. And because of that direction in mind, I'm going to say A is connected to B, but B is not connected to A. Take a look at this. B is connected to G, but G is not connected to B. B is connected to G, but G is not connected to B. This is a directed graph, and that's the adjacency matrix. You could potentially have weighted graph. A weighted graph is going to actually show you how much a single connection between two nodes are going to be important in the overall process. It is extremely important when you want to actually consider causality, for example. So in this case, A and D are connected. We are quite conscious and aware that there is no direction from D to A or A to D. That means A is connected to D and D is also connected to A. But also, we already know that the weight of that connectivity line is going to be 12. Who is going to assign this? The expert. The expert in the domain is going to actually assign that kind of weighting factors. Sometimes these weighting factors could potentially be modified dynamically within the program. You could potentially start with an initial weighting factors for all of the lines with an objective file at the objective function at the end. And the objective function at the end could potentially, which is usually an error function, could potentially force you to go back and change the weight so that the overall error function is going to be reduced and to be less than a factor usually we call epsilon, the error factor, okay? Now, as you can see, A and E has 12. A is connected to E by 12, and E is connected to A by 12. A and B, A is connected to B by 8, B is connected to A by 8. This is a weighted, undirected graph. Weighted, undirected graph. Of course, we could have weighted, directed graph at the same time. So this is a weighted directed graph and the adjacency matrix. If you take a look at that, 1 is connected to 2, 1 is connected to 2, and the weight is 1. 2 is not connected to 1, but in this matrix, we have decided, this is one fashion of representation, to decided to make it a mirror, except that we are going to put it as a minus sign. You could potentially put it 0 here. So this one, 2 to the 1 is not connected. This could be 0. 3 is not connected to 1. You could potentially put it 0. But in this one, this fashion, we decided to simply choose a different approach. And the approach is whatever you see on top of the diagonal component, we are going to have it on under the diagonal component with a negative sign, with a negation in place. This is -1 and this is 1. So essentially, we are saying 4 is connected to 2 by -1. And if this is the case, I'm going to have on a mirror fashion, 2 is connected to 4 by 2 is connected to 4 by -1, and 4 is connected to 2 by 1. So this -1 means that the directed line is supposed to go the other way. It's supposed to be this way, not this way. So these are all our rule book. You could potentially define your own rule book for as long as you remember what you have identified and presented your graph into a matrix. You should be okay continuing with the coding. At some point, you may realize that your matrix representation may not be as efficient as any other technique. You may go back and change your rule book and change your matrix representation. Adjacency list. In the computer science, we usually would like to understand that from you see, the computer cannot understand this graph. This graph has no meaning for the computer. Computers doesn't have an eye. Even if you put a camera, still it needs to understand the connectivity and translate that to what we call 0, 1. So we need to facilitate that translation from a visual confirmation, visual inspection of the graph into a list. Now, if you take a look at this, 1 is connected to 2 and 3, 1 is connected to 2 and 3. This directed graph means nothing. It simply says 1 is connected to 2 and 3. You could potentially put 1, 3, and 2 if you wanted to. But the reason we put 1, 2, 3, because we wanted this to be incremental. 2 is connected to 4, so that's 1. 3 is connected to 4, that's okay. Again, the incremental. That's a rule that I have assumed. I'm going to apply incremental of 4 to 5, 5 to 6, and 6 is connected to nothing. This I could potentially understand better as I try to code my case. So adjacency list. Do I have a project for you with adjacency list in this class? No, but you're going to know adjacency list because in the follow-up classes, you need to know this terminology. Adjacency list could potentially be translated a little bit more down the line in terms of the computer understanding, the computer language. Here is you have an H1 graph, you have an H2 graph, you have 0, 1, 2, and 3, no direction. 4, 5, 6, 7, no direction. This is the head node. The head node is something that I would be utilizing in my code. 0 is connected to 2, and 2 is connected to 1. Remember that I would potentially populate this when I need this for several reasons. So at this time, node 0 is connected to node 2, and obviously node 0 is connected to node 1. I could potentially have had 1 here and 2 here, if I wanted to do incremental representation. If you take a look at the 3 is connected to 1 and 2, so I'm going to have 3 divided connected to 1, and this is supposed to be 2. So this one is a simple mistake. This is supposed to be 2. As you can see, the last one is 7. 7 is connected to 6, but obviously that's the only connection that 7 has. And 6 is connected to 5 and 7. 5 is connected to 6 and 4. We facilitate the process for the computer to understand the representation of that graph. So we are doing a reverse job. Sometime you want to allow the human brain to understand, because obviously human brain is extremely complex. We have not had any success in replicating a brain with all its complexity yet, functionalities that it has. So if I wanted to understand what the numbers mean, I'm going to make it visualize. I'm going to visualize the process. So if you take a look at this, this is going to be helpful for me if I wanted to bring a brain in the process to understand that. But if this is a graph and you want to talk to the computer the other way, you need to actually present it in a in a fashion that could be understood by basically by computer. This is a sequential representation. Again, the same graph that I had in the previous page. I could potentially represent this instead of having so many rows and columns. I could potentially represent it all in one row, but with a specific rule. Who defines that rule? You define it. But there are some common rules that have been utilized in the past, and you can potentially follow up their footsteps and to see whether that's going to help or not. So how many nodes do I have? 1, 2, 3, 4, 5, 6, 7, 8. So I have 8 nodes. And if I want to talk about any of the nodes, I cannot talk in the frame of 8. So when I say 0, I need to utilize all the way to basically 8. And I'm going to actually start talking about 0 in the place of 9. So when I say 8 plus 0, 8, how many? You have 8 nodes plus 0. Then you're talking about 0 in the cell number 9, and this is how you're going to put a pointer. Again, it's a rather a strange way, but the computer says, okay, let me take a look at the number under the 0. It's 9. Let's go to cell number 9 and then take a look at underneath. 0 is connected to 1 and 2. So 0 is connected to 1 and 2. I'm going to dedicate these 2 cells to 0. What cells? 9 and 10, because I have 2 connections, okay? So 0, go 9, then all the way to 9, then tell me about the connection. Connection is 2, connection is 1. So 10 and 9 are both taken for node 0. Let's take a look at 1. Remember, 10 and 9 are taken. So if I wanted to talk about 1, I need to talk about the next cell. I can't talk about 9 and 10. It's already taken, reserved for node 0. So 1 will be 11. Now 1 is connected to 3, 1 is connected to 0. So I have 2 nodes connected. This is undirected graph, so I'm not worried about it. So 1 is going to be 11. So the way computer thinks is this. You have 1, go to 11, go to cell 11. Cell 11 is going to tell you 0 and 3 and 0, because 1 is connected to 0 and 3. So I'm going to use 0 and 3 here. So I have 2 connections to node 1, and therefore 11 and 12 are going to be dedicated to node 1. You cannot use that. These are already reserved. When you go to node 2 cannot utilize 9 and 10 because reserved for node 0, cannot use 12 and 13 because it was reserved for node 1, and therefore 2 needs to start from 13. So 13, this 0 is actually the connection for node 2. So if you take a look at the 2 is connected to 0, 2 is connected to 3. So 2, computer, go down, 13. 13 is my cell. Which are the nodes? 0 and 3. This 0 and 3. Okay, so this is going to explain to me that 2 is connected to 0 and 3. Now, 13 and 14 is reserved for node 2. I cannot use 13 and 14. So if I wanted to talk about 3, I need to actually address cell 15. So 3, 15, 15 is going to be a cell here, and I'm going to be talking about 1 and 2 as the connection. 15 is going to take these 2, 15 and 16 are going to be reserved for node 3. Let's try this one more time. Node 4 is only connected to 5. So remember, 15 and 16 are already reserved. So when I talk about 4, I'm actually talking about, I'm referring to cell 17. In the cell 17, I only have 5, no more. So only 17 is reserved for 4. And therefore, when I talk about 5, I could potentially start from cell 18 right after. And 5 is connected to 4 and 6. So I'm going to have 6 and 4. 18 and 19 are going to be reserved for 5. And 6 is going to be referring to cell 20. So 6 is going to be 5 and 7, 5 and 7. And 7 eventually is going to be 6. And it's going to be the last of them. It's going to be 22. And that's going to be connected to 6. You could have your own way of representing the connectivity graph. So you could potentially represent them in the form of matrices, and you could potentially represent them in a form of a vector instead of matrix, which is going to be 2-dimensional. This could potentially become, this is still 2-dimensional to me, this is still 2-dimensional to me, but this is going to be 1-dimensional for us, okay? Incidence matrix. Let's take a look at this. I have A and B connected through E1. This time I'm not having node and node. This is node on the row side. So row A, row B, row C, row D, row E, which seems to be vertical to us, but this is row labeling. But then it's about edges. E stands for edge. So A and E1, that's the connectivity. So it tells me that E1 is connected to A. If you take a look at A, E2 is connected to A, so that's going to be 1. And then E3 is entering, and therefore it's going to be -1. Again, that's my rule. You can define and modify and change the rule. Show me that your definition of rules that you're following is going to be more effective. You're more than welcome to define your own rule. But this is something that the industry has been using in a number of topics, in a number of research. Take a look at B. E1 is entering, so that's -1. E6 is leaving, that's +1. E4 is leaving, that's +1. So let's take a look at B. E1 is entering -1. E4 is leaving +1. E6 is going to be leaving +1. And I actually created what we call incidence matrix. Okay, I'm going to stop now, and I'm going to go into next part, which would be part 5.